Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last two classes, we are learning about the organolithium. So I taught you about the metal halogen exchange in the last class. So in today, I'm going to talk about another important method where you can generate organolithium species through deprotonation, and there will be something called a directed metallation. So you see different type of strategy we have used to deprotonate it from the sp3ch or from the sp2ch. So we're going to learn about the lithiation alpha to the heteroatoms. So you see how the heteroatom affects this type of lithiation. We're going to learn about the directed metallation, the orthometallation, some sort of a stabilization factor for this type of reaction, and then the anionic Fries rearrangement, and also we're going to learn about something called the lateral lithiation. So you will see sometime the kinetics and thermodynamics going to play a very important role for this type of lithiation reaction. Again, these are the topics I'm going to cover here. So first thing is we are going to learn about that if you have a nitrogen or oxygen atom, then what is going to happen? The alpha to that Ca is going to get abstracted. Now the problem is, now if you are talking about something like that, like if you have a scenario like this, so these R groups are playing a very important role here, because if you think about the nitrogen having a lone pair here, now we are talking about that if you use a corresponding alkyl lithium, it is going to abstract this proton. Now it is only going to abstract this proton once you have R groups, will have some sort of electron withdrawing group, because otherwise once you go for this, once you treat RLI and once you generate the product, let's try to understand what is the things going to happen. That you have this lone pair and you have this carbon ion, correct? So now this going to repel, because you have now a lone pair and a carbon ion, they are going to repel. To stop this repulsion, what you have to do, you have to attach with some group on the nitrogen or oxygen which can pull the electron density of the nitrogen. Okay, that's why what we are saying, that if you have a nitrogen lone pair can coordinate strongly with an incoming organolithium reagent, that is good, because nitrogen will be going to, because nitrogen will be some sort of a Lewis basic, and you have a Lewis acidic lithium, so that is going to coordinate with the nitrogen, so that is fine. But the next thing is you have to understand there should be a, but the direct deprotonation will be impossible as long as you are not putting electron withdrawing group. Okay, so there will be, of course, there will be antibonding interaction of carbon lithium bond with an to the antibonding interaction to generate this corresponding lithium. So that's why you will see here we are talking about some sort of a stabilizing effect, that if you have electron withdrawing group attached here, now what has happened, now you can see now this, the nitrogen lone pair will be pulled towards the carbonyl group here. So now what is going to happen, this, now it is going to form this corresponding lithium. Okay, there is couple of important thing here. One is you can think about that this is pulling the electron density. At the same time, once you have this NCO, that can also make a stabilizing interaction with the lithium. So there is first the lithium is approaching, then it is going for this deprotonation to deprotonate this acidic proton, and then it is getting some sort of a stabilization as well with the chelation. Okay, so the chelation is an important factor, and for that you have to also introduce a acetyl group to get the electron density from the nitrogen, and as well as it can make a some sort of a chelate with the electropositive lithium. So here again some example here, you can see this particular amide here, you can see this is a carbonyl, this is the ketone group which is pulling the electron density from this nitrogen, and then once you are able to deprotonate here, once you deprotonate this CH and generate this corresponding lithium in terms of LDA, then this lithium is also getting stabilized. Okay, so that stabilization is very important. As I mentioned at the beginning, that in case of the metal halogen exchange, also I have explained you that the stabilization of the carbon, the corresponding lithium which is forming is a very important for the driving the reaction towards the right hand side. Here also you can see this stabilization is a very important factor here. Okay, so you can see here there are different type of variation. I think I am going to only cover few slides here, but you will able to get a lot of question in the practice, so where I can supply some of the questions on this particular topic. You can see here it could be a 4-member ring, it could be a 5-member ring. Okay, so you have seen that if you generally if you have there could be different type of protecting group here. It could be a A Bock protection, that can also here also it can act as a directing group. The lithium can be directed through this to abstract this CH. Lithium can be directed through this oxygen to abstract this CH to form this corresponding lithium here. So this CH will be replaced to get corresponding lithium. You can see there are several different things, several different variations, but in every cases one of the thing is very common, that you put a electron withdrawing group with the nitrogen, and that oxygen is also acting as a chelating agent here. Then there is an example here. In this particular cases, what we are seeing in this molecule, there is 2,4,6 tri-isopropyl group. So once you have isopropyl group and you have this amide here, now once you have this lithium, the thing is the lithium going to coordinate with this oxygen, as you can see here. So these things you can see, once the lithium going to coordinate, there will be change on this. What is going to happen if there, so there will be this bond going to get weaker, so that's why the frequency going to get decreased from 1650 to 1625. Now what is going to happen here, as these orthoprotons are already not there, is replaced with a isopropyl group, that's why it is going to abstract proton from this N-methyl, okay, through a coordination. And now once you are forming the corresponding lithium, the lithium is also getting stabilized through the coordination with the oxygen. As I said, lithium is electropositive, it can make a coordination, so that will make a stable organolithium. Now we are going to learn about the oxygen. So what will happen if you have an oxygen atom and there is a CH here in this particular compound. So we have learned about the nitrogen. Very similarly, the oxygen will be have a OCONR2. That means you put some sort of a you made some sort of a carbamate here. Okay, the first thing is from alcohol, you made the from alcohol you can make this corresponding carbamate. And once you make the carbamate and once you treat with the the sec-butyl lithium and timeda, that can able to abstract this particular proton. Now we are talking about the next to sulfur, that if you have this compound, one side of sulfur is phenyl and one side is methyl, then in case of the Bewley Dapko in THF, that is going to abstract this proton here to form this corresponding lithium. Okay, so that is happening through this interaction with the sulfur carbon sigma star. So that's how they are generating this. Again, you can see there are some example here. There are several example for generation of this type of organolithium species. Once you have this type of allyl species here, that can so this proton will be the acidic proton. So here it is forming the corresponding lithium, and here you have pyridine nitrogen, that is electron deficient, that can make some sort of a chelate complex here. Okay. And if you have oxygen like something like this, some sort of a thiocarbamate here, then you can see again here also formation of the lithium, and that is getting coordinated with the corresponding oxygen. So now we are talking about silicon. So here if you have a allyl silicon, allyl silane, if you treat with the butyl lithium and timeda, it is going to abstract this proton here from this position to generate this corresponding lithium here. Very similar thing, if you have a benzylic group here, then again this proton, this carbonyl will be even more stable. So it can be stabilized in two effects here. First thing is that it's a benzylic or allylic, and the next thing is the silicon has a alpha effect. We have already learned about this, the silicon alpha effect, and we're going to also discuss that once I'm going to teach you the organosilicon chemistry. That the if you have this, the sigma orbital of this corresponding lithium is interacting with the carbon and silicon sigma star antibonding orbital. So this sigma orbital is interacting with this sigma star orbital here, the carbon silicon sigma star orbital. So that overlap actually stabilizing the anion alpha to the silicon. Okay, so there is another example here. In this case, what is happening, again you can see here in case of LDA, so this is acting as a directing group to abstract the proton from this, okay, through chelation, because again you can understand now that how this directing effect is important, that once the lithium is getting coordinated with the electropositive oxygen, so he is finding the nearby protons. Now he found this, the CH3 proton, which is getting abstracted to generate corresponding lithium here. Again the alpha effect is also another important factor here. So now I am going to talk about the different type of directing groups. So all this type of the directed metallation, what do you find out that in directed metallation, this this type of directing group is have a common nature, that have some element which is electropositive, so that, or it's a Lewis basic. So that means if you have a Lewis basic, then you have a Lewis acidic lithium going to coordinate with that. So that some sort of a coordination going to happen between them. Once that is going to coordinate, now if you have a RLi, suppose, then you can think about, so this is the proton and you have a Li, and if you can write this way, then you can think about that, because it is getting coordinated, this R can come and take this H and to generate some sort of an anion here. Okay. And then also another important thing, that you have this type of electropositive element here, that is going to also form some sort of a chelate to stabilize this carbon ion. As I mentioned, the stabilization is very important. Now you can trap with electrophile to get to the corresponding product. Again, you can see here that the difference is that if you have normal just like benzene, and if you treat the butyl lithium, you will not find that corresponding lithium, phenyl lithium formation happening. But as soon as you put a directing group here, things become very important, because the stabilization of this lithium and is very important, and most of the time you will find out that all this type of directing groups has a very common thing, that they have a stabilization effect of the corresponding lithium. That is the important thing which is missing here in case of benzene. That's why, because of the stabilization effect, you can write this like that. Because of the stabilization effect, this type of reaction is happening very fast, but you will not find this reaction happening once you don't have any stabilizing group. So here are the list. I think the list could be even more. You can see different type of groups we are talking about here. Most of the time you will see there will be a carbonyl group, which this oxygen is the one which always going to form a chelate with this lithium, or there will be a carbon sulfur, again carbon oxygen bond, oxazolene. And so these are the one which are very strong going to bind here. So if you have this type of directing group, the reaction is going to happen fast to form this corresponding phenyl lithium. But if you have CF3 or the corresponding aldehyde or the OMe, so these are also very important. So here also the lithium going to bind to go for some sort of, you can see, because you have oxygen electron rich, lithium is electropositive, so that can bind here. And if you have a R group, that can abstract the ortho proton here. Okay. And then in case of these groups, they are weak, of course, compared to this, because these are not even connected here. But you are going to see in one particular class here, which is this one, once you have a NN dimethyl, or if you have a NR2, in this particular class, actually lithium, because of the nitrogen electron very rich, it can coordinate here and it will go for a metal halogen exchange. We are going to talk about that also. So first thing, if you see in case of this particular oxazolene, you can clearly see this carbon double bond N, this imine nitrogen is now coordinating with the lithium, which is electropositive, and now this CH bond, so this CH bond getting broken, then it is going to generate this corresponding organolithium, which can trap with CH3 iodide to introduce CH3 group there. Okay. So this directing effect is allowing to abstract this orthoproton, not the corresponding paraproton. Okay. So in case of the pivalonide, so this is a if you start with the corresponding amine, and then if you make a block protection of it, then what is going to happen? Now this can act as a directing group here, but you have this NH which is going to abstract first, and then once you have another equivalent of butyl lithium, so you need two equivalent of butyl lithium here, because you have acidic proton in the directing group. So now what is going to happen? Now the N-butyl lithium going to make coordinate with this lithium, going to coordinate with the oxygen. It is going to get rid of this orthoproton to form this corresponding lithium, which is going to trap with a methyl iodide. As I mentioned, if you have a dimethylamine here, so benzyl dimethylamine, I think I was telling you in the previous slide, then that acts as a directing group here nicely, because you can see, because the nitrogen is electron rich, it has a it can coordinate with the lithium very nicely, and that can allow you for the directing to abstract this CH bond here to generate this corresponding lithium, to clip this corresponding CH bond to generate a lithium after the proton abstraction to form this, which can form the lithium, which can go to the act to the corresponding aldehyde. Again, if you have the N-cumylyl benzamide here in these particular compounds, using the sec-butyl lithium, the first thing it is going to go for here also it is going to go for a proton abstraction, and then it is going to abstract this through a reacting effect of this carbonyl group here, okay, it is going to generate this corresponding lithium, which is going to add to the corresponding aldehyde. Again, I think here you can see also this NH, which also going to convert to the corresponding lithium as well. And once you treat with the aldehyde and H3O plus, it is going to get to the corresponding product here. So now we are going to talk about the reacted lithiation of pyridine, because pyridine is itself is electron deficient. So now if you try to, and so the problem is, if you take a organolithium and treat with pyridine, what is going to happen? It is going to go for a 1-2 addition. Okay, it can add to the C2 or in the C4 position. So that's why if you want to go for a proton abstraction to generate a lithiated pyridine species, then reacting group is very important. So that you are allowing the lithium to coordinate with the reacting group first, and then it can able to go for a proton abstraction to generate this lithium, which can trap with the corresponding electrophile. So there is an example here given that if you have a reacting group here, it can able to abstract this corresponding lithium, then it can trap with the electrophile. Or if you have a in a para position, if you have a reacting group, then it can form the lithium in the meta position to get to the corresponding product. And again, there are several different type of reacting group is used here. So one question you might be thinking, sir, why in this particular reaction, when you have a reacting group in the meta position, why you are abstracting the proton from the C4 position, why not from the C2 position? Okay, so the one of the major important thing here, that once you abstract this, now once you generate a carbon ion here and once you have a nitrogen have a lone pair, there is a repulsion between them. So this carbon ion and this lone pair of nitrogen have a repulsion. That's why if you see the rate of abstraction of this pyridine proton, and if you think about the C4 come first, then the C3 and then the C2. Okay, so this has much higher rate compared to a C2 because of this. And now we are talking about that the ortholithation reacted metallization happening because you are forming a more stable lithium. So that is again we are trying to tell you here that if you have a sp2 hybridized versus a sp3 hybridized, so this is having more s character, more stabilized. That's why this reaction driving towards this side. It cannot come back in this direction, that the phenyl lithium will take a hydrogen from the butane because of the stability. So here we are talking about that if you have a butyl lithium and a timeda versus if you are butyl lithium alone. And in these two substrates, what is happening? The deprotonation happening from this position if you have a alone butyl lithium. So what is happening? You can you clearly know for this particular compound, if you have a butyl lithium, the lithium going to coordinate here. Now the butyl, the minus going to abstract this particular proton to generate this corresponding abstract. So it's going to cleave this carbon hydrogen bond to generate this corresponding carbon ion in this position. Okay, but once you have a the butyl lithium and a timeda, now your butyl lithium is already having this type of structure. I think I already explained you in the previous classes that once you have a timeda and butyl lithium, it forms some sort of a dimeric structure. And now what is happening? Now once it's trying to abstract a proton, it is finding out that where it is going to abstract. So based on these two proton, if you see, if you are thinking about this particular proton, then we have already learned that if once you have a OMe group here, the carbon ion will be more stabilized. So now the reacting effect is not playing the important role. Now the inductive effect, the minus I effect of the minus I effect of the OMe group actually playing the role here once you have a timeda. And once you have the butyl lithium alone, then it can coordinate. So the reacting, so there is a two thing happening. One side there is a reacting effect is playing a role. One side the stability of the negative charge is playing a role once you have a timeda bound with it. So here again it is shown that once you have an anisole, and it can actually convert the hexameric structure of butyl lithium to a tetrameric butyl lithium anisole complex. From there the timeda comes into the play, and then it can. So if you are using this particular anisole, you are trying to deprotonate, then people use the timeda with the N-butyl lithium. What is going to happen? That can break down to a butyl lithium timeda dimer, now which can able to abstract so this proton to form this corresponding lithium, which can stabilize through the OMe group. Again here you can see here, we are showing here that's corresponding, so it can also form a, as I mentioned at the beginning, once you have oxygen, nitrogen, it can form some sort of a chelate, because this is the electropositive, it's electronegative, and then it can take this hydrogen and then form this corresponding organolithium here. So you can write in general here that if you have a, depending on the X group, if you have oxygen, nitrogen, all these type of groups, or if you have a CH2, NME2, all these cases, it is going to form this corresponding lithium here. So now you can see that we are talking about here the relative heat of protonation. So the stabilization afforded to an ortholithiated anisole relative to a para-lithiated anisole. So here you can find out that the rate is getting decreased in this direction, because you can see the heat of the protonation, the value is getting decreased because the stabilization. So the formation of the corresponding lithium stabilization is the driving force, as I mentioned. So if you have two methoxy group here, then it is going to abstract not this proton. The proton is the middle of these two methoxy, because now it can able to form a more stabilization through both the methoxy group. Okay. Now if you have a ortho, which will be the next, if you have a para, then of course it will be the lowest than that, and then if you have a only phenyl lithium, it will be the lowest there. Okay. Very similar thing happening in case of the naphthalene here. So there is a, we're going to come back to that also, that here if you going in this direction, so this direction they are more stable, this direction they are less stable, because here you can see your lithium is in the para position, so there is no coordination between the lithium and the methoxy. So here you can see if you have this type of directing group here, as I mentioned in the before, that your lithium can able to coordinate with this oxygen. Now you have R, which can able to take this H to generate this corresponding lithium, and now this will be forming a chelate complex, the lithium with oxygen, and you can able to travel with the electrophile. So here this is an example, if you have a sulfur versus you have oxygen. So the the diaryl sulfide are lithiated ortho to sulfur, but less efficiently than the diaryl ether. Okay, so once you have the oxygen here, as you see, compared to oxygen and sulfur, now the oxygen will be able to coordinate with the lithium more, so that will allow this formation of this lithium, corresponding lithium, and then in the corresponding product much faster compared to the sulfur. So now I am going to talk about a ortho-Fries rearrangement. What is going to happen for this particular reacting group? If you have some sort of the diethyl carbamate, NN diethyl carbamate, if you use carbamate as a reacting group, then this corresponding lithium is not stable. Once the corresponding lithium is going to form, this lithium going to go for an intramolecular reaction. It is going to attack here, and then it is going to come back, and it is going to cleave this oxygen carbon bond to generate this corresponding OLI, which is going to go at proton to get to the corresponding OH. So what is happening here, if from starting this compound you synthesize this corresponding phenol, okay, that is going through this type of anionic ortho-Fries rearrangement. Okay, so here it is acting as a reacting group, at the same time it is getting attacked and cleaved to get to the corresponding product. Once you have a naphthalene, in case of naphthalene there is two different scenario. So if you have a, suppose you started with this, so in case of naphthalene things are little tricky, and selective lithiation is still challenging. So suppose if you have a OMe group here or here in this, or in the alpha or beta position, what is going to happen there? There is a two different proton. Okay, so if it is happening from, so we can give them that this proton not acidified by X but close to RLI. So this is one thing, this proton is but also close to RLI, and we have given them as a perilithiation or ortholithiation. That means it can, if you think about this this proton abstraction, then if you generate a negative, this OMe can stabilize. So that is how it is forming the ortholithiation. You will see that the ortholithiation is happening in a major, but at the same time there is the perilithiation is also happening. Okay, because why this is happening? Because of the, because once the lithium is coordinating here, now it can able to abstract this proton and then formation of the lithium here as well. So that's why if you see in the literature, if you are going for this type of the lithiation of the naphthalene with a some sort of a X means some sort of a directing group, like a, you see a methoxy or things, people have, end up getting a mixture of product. I think the same thing I was trying to explain in the previous slide, that if you have a like a directing group here in the 3 position in case of pyridine, why it is abstracting the CH, the CH from the C4 position, not from the C2, because of the problem is the deprotonation accelerated, but the product is destabilized. Once you have this product corresponding lithium and this, so they are going to be repel each other. That's why the relative, as you can see, it's 700 times faster than this one. So here again, if you are electron deficient 6-member heterocycle, then not only the LDA, other lithium amides are capable of deprotonating with it, because you can see what is happening here, because you have a directing group. So that's why, and also it is a electron deficient. That's why the other lithium amide are also capable of abstracting this the proton from here to generate this corresponding lithium. Okay. As I mentioned that if you are not using the directing group, then the organolithium can attack to the pyridine, because pyridine is electron deficient. So here you have some sort of a 5-member aromatic heterocycle with electron rich atom like oxygen, sulfur. So what is happening in these cases, this can also chelate with the lithium because it is electron rich. And now you can see this is the proton next to that, it is going to get, if you have butyl lithium, this can form the corresponding lithium, which is the furan C2, or in the thiophene C2 position. Here if you have a pyrrole, you have to just protect the pyrrole in methyl. Now it can also form the corresponding lithium using the butyl lithium. Again here you can see, if you put instead of the N-methyl, if you have the N-BOC or some sort of a other protecting group here, that can be deprotonated first. If you have this NH tarbutyl, that can be deprotonated, then another equivalent of butyl lithium can able to deprotonate that. Okay. Similarly for furan and thiophene, as I mentioned, it can able to form this corresponding lithium. If you have a indole, then the things are interesting, because indole have a NH. So first thing, if you give an N-butyl lithium, then the idea is you have to first, so this proton will be abstracted to generate this corresponding lithium, which will trap the CO2 to form this lithio-carbamate. So now if you treat with the corresponding tarbutyl lithium, that can go for a C2 lithiation. So in indole, if you want to generate a C2 lithiation, then you have to treat with an N-butyl lithium first to get rid of this NH, so then it will form the corresponding carbamate in place of CO2. Then once you use the tarbutyl lithium, now it is going to form the corresponding C2 lithiated species. So here you can see that, and then there is another important fact about indole, that if you put a bulky group with the nitrogen, that means what is happened, you are stopping this coordination of the lithium here, because once you have a bulkier group, the coordination will not be good enough, and you are using a tarbutyl lithium, you are using a bulky lithium as well. So bulky lithium and the bulky protecting group with nitrogen, now it will end up forming a lithium in this position, because you can see this is the next proton which are acidic, which can be brominated further. Then we are going to talk about the lateral lithiation. So if you have some sort of a benzylic group here, and you have a directing group in the benzene ring, okay, then what is going to happen, it can able to abstract this proton from here, okay, to generate this corresponding lithium, which is going to form some sort of a chelate to stabilize it, and it going to form, it going to react with the corresponding electrophile. Again, this type of inductive electron withdrawal is a very important thing here. That is another important factor for this reaction going towards the product. Or there is another thing called conjugation. So we are going to come to this factor. So there is inductive effect versus a conjugation. So this is an interesting example here. In these cases, so if you see CO NET2 and then you have a CH3 groups in the para position. If you treat with the seg-butyl lithium with TMEDA, then there is a ortholithiation happening here, or like orthometallation to form this corresponding lithium. It's a kinetically controlled product happening at -78 degrees Celsius. And if you go to a 0 degree Celsius, then what with the LDA, then it is forming the thermodynamically controlled product through conjugation. So this is stabilizing through the conjugation, because the negative charge is getting stabilized through the conjugation. Here the negative charge is getting stabilized through the formation of a chelation. So what is happening here, once you use the seg-butyl lithium in TMEDA at the low temperature, the oxygen is the one who is going to chelate with the lithium, and that is going to direct this abstraction of the CH to form this corresponding lithium here. Okay. So here the coordination is the most important thing here. But once you use LDA, you can see that there is a difference between the structure and the LDA and the segmental lithium. In case of LDA, what is happening now here, because LDA is also a bulkier in the structure, so it is going to find the proton which are acidic here and which is going to stabilize, also getting stabilized. So if you form this carbon ion, this is getting stabilized here. That's why, and so here what is happening, the CONH2 is kind of acting as electron withdrawing group through a minus I effect to stabilize this carbon ion. So one side there is a minus I effect of stabilization, one side there is just chelation control stabilize. Again, in this particular example, if you have a group in the ortho position, not in the para position, then you are getting both the effect. You are getting both the chelation effect as well as the conjugation effect here. That means what is happening, what I am trying to say here, once you are lithium is here, it is have some sort of a chelation effect which can abstract this CH proton to form the corresponding lithium, as well as this lithium is also getting stabilized through the conjugation. Okay. So both the effect is operating. So this is happening very fast. In this particular topic, what I have tried to cover the deprotonation reaction. Okay, so how to generate a corresponding lithium through a deprotonation. And I started with the deprotonation once you have a different type of heteroatom like oxygen, nitrogen, sulfur. Then I talk about different type of directing group for the orthometallation, and I have shown you different type of example here in this particular topic. And please go through this type of reference books here for your more knowledge, and there will be a lot more example which is given. Again, thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.